Thank you, Sunny. And thank you also for giving a brief introduction, at least showing two beautiful pictures of those minerals at the beginning in your talk. And how did it advance already? That was weird. So again, I'm Laura Grace. I'm at CU Boulder. I'm going to be talking about these alunite jarosite minerals. If you're like, I don't know what these are, don't worry. I will explain what they are and why you should care about them. So this story starts on Mars, where in 2004, Opportunity identified the mineral jarosite at its landing site. Here you're seeing Opportunity looking back at its big balloon thing that it used to safely land. And this was a really exciting discovery. We knew that there were tons of sulfates on Mars. We'd seen them from orbiters. And it had been hypothesized that some of those sulfates were formed through acid sulfate alteration. But the discovery of jarosite pretty much cinched that. Jarosite requires pretty much acid sulfate alteration to form. And as the name implies, acid sulfate alteration involves very low pH and a lot of sulfur to alter that starting material. In the case of Mars, that's basalt, pretty much. And so jarosite meant, gave away the punchline. Jarosite means that the environment on early Mars would have had to have been very acidic. We're talking a pH of 3 or less at the sites where jarosite was found. It also means that the environment has to be pretty water limited. Otherwise, it would continue to react and form minerals like hematite. And it also has to be a pretty highly oxidizing environment. And very significantly for astrobiology purposes, jarosite can be made by microbes. Microbes can get involved with the oxidation of iron and sulfur. So this was a pretty exciting discovery. But if you recall, how are the slides advancing without my touching them? That's... Oh, weird. Okay. So that's good to know. So we've got alunite and jarosite are members of a mineral group. If you recall, I mentioned that I'm talking about both of them today. And they've got this mineral formula where we've got a potassium or sodium. Any cation really can go in that A site. These are the two that matter here, aluminum or iron in that B site. And then we got some sulfate and hydroxide. And in that A site, if it's a sodium, then it's, we're gonna call it natro something. If it's in that B site, if it's iron, then that means it's jarosite. And if it's aluminum, that means it's alunite. And these definitions work pretty well because for most of history, we didn't really find anything that was intermediate between these. We were only finding the end members, where that B site was either all jarosite or that B site was all aluminum. However, that changed recently when Tom McCullum and others went to Cerro Negro, and they actually found stuff that was intermediate between these end members. So what I'm showing you here is a plot from his 2013 paper. You've got aluminum per formula unit on the x-axis. You've got iron per formula unit on the y-axis, and I just noticed that he misspelled formula in his paper, and and I didn't notice. And in the gray boxes, the gray triangles, you see kind of the literature group. So these are the classic alunite, classic jarosite, and then these 6 samples from Cerro Negro that he's showing you. Most of them fall in those gray triangles, but 2 of them, the blue triangle and the red circles, actually kind of span that intermediate range. And why this matters is that when he looked at these with Mossbauer, which is the instrument that Opportunity has that they used to identify jarosite, these all looked indistinguishable from jarosite. Mossbauer only looks at iron, and if you've got iron in your alunite, it's going to look the same as jarosite, even if that's only a little bit of iron. So this led to some of the following questions. First off, now we've found what I'm going to be calling iron-rich alunite. You could call it aluminum-rich jarosite. For consistency, this is what I'm calling it for the rest of the talk. And if we find it at several sites in Nicaragua, is it a common alteration product? Are we going to find it at other sites? Are we going to find it perhaps on Mars? And if we do find it on Mars, what does that mean for the environment on ancient Mars? I told you what jarosite meant for the ancient environment. It had to have very low pH, highly oxidizing, pretty water limited, but we don't know, well, I will tell you what it would mean if it's iron-rich alunite instead. And lastly, how can we distinguish between jarosite and alunite and these intermediate species on Mars, using instruments that are on Mars now or will be on Mars in the near future? Whoops. So to answer these questions, I'm going to show you some results from 3 different volcanic analogs for ancient Mars. These are Cerro Negro in Nicaragua, Poas and Turrialba in Costa Rica. And a lot of the data I'm going to show you comes from XRD. Thank you, Svet, for giving a brief introduction to that. And we've got this beautiful little field instrument on the left. This is called the Terra that can actually come out into the field. You're seeing it in this image actually within the Turrialba crater. And this was specifically designed to be analogous to Beckerman on MSL. So it's analogous to the XRD instrument that is currently right now on Curiosity. And so I'm going to show you some different temperature and pH regimes that I've kind of identified. They're present at pretty much all 3 of these different volcanic analogs at several different sites within these volcanic analogs. In this first site where you see me at Cerro Negro, I'm zooming in on what I'm looking at, as well as at Turrialba. If we've got a temperature of about 80 to 100 degrees Celsius, pH of 2 or less, we see a lot of silica minerals. Cristobalite is a high temperature version of quartz, amorphous silica. We see some sulfates like gypsum and natural alunite, wink wink, as well as some sulfur that hasn't been fully oxidized. Again, I'm drawing attention to that natural alunite. And if you recall, natra just means it's got sodium in front instead of potassium. And I'm going to call those sites hot and acidic, and my computer's going on without me. The next site is kind of site has 50 to 100 degrees Celsius, pH maybe 3 to 5, so we're going a little down in temperature, a little up in pH. These sites have gypsum, a sulfate, amorphous silica, cristobalite again. You're also seeing plagioclase, which is a mineral from that starting basalt. So that's stuff that hasn't gone fully altered, as well as hematite, so an iron oxide. Again, I'm going to draw attention to that natural alunite. And although this is obviously relative, I'm going to call this moderate. For these kinds of sites, this is moderate. The next kind of site, we're talking about even lower temperatures, things you might actually be able to tolerate. Here, natural alunite is actually the most dominant mineral. So I've just been showing you, in fact, actually the most dominant minerals that are found in 25% more of the samples from these sites. And here, natural alunite just the most dominant of all. We're also seeing some pyroxene, which is another like plagioclase mineral and basalt, goethite, which is another iron oxide. And I'm actually zooming in on this patch of natural alunite there with my little knife next to it. And I'm calling these dome edge or crater rim. And the last site I'm going to briefly talk about is kind of this fluvial outwash site. So these are sites that we basically are just seeing stuff that rain has just kind of brought down to the central crater, and it's just kind of flowed in there. So again, natural alunite is most dominant here. We also are seeing clays that are forming here with all of that nice water. I'm still investigating which kinds of clays. That's work in progress as I speak. Unfortunately, though, we don't know exactly where these may be from. They could have been washed down from any part of the crater rim. But still cool that natural alunite is most dominant here. So I'm going to quickly tell you this formula, which basically just says that Fe number is the percentage of iron in that B site. That's all you need to know here. So that B site can have aluminum and or iron, and Fe number is how much iron. So I'm showing you here now a plot of those three of those different environments I showed you. The hot and acidic, which is pH less than 2 or less than or equal to 2, temperature 80 to 100 Celsius. That moderate conditions, which is pH is 3 to 5, and temperature about 50 to 100 degrees Celsius. And that dome edge with kind of an even lower temperature. And I'm showing you the Fe number for samples from 2 of those volcanic sites, Turrialba and Poas, that I determined with either electron microprobe, EMP, or the SEM EDS. And here you're seeing that some of these are really concentrated, either pretty close to 0, so pretty close to the literature values of alunite, or for some of them, it kind of spans a huge range. So that iron concentration can be anywhere from 0 to even higher than 20 in some of these samples. And what you actually know, if you notice that there's like different kinds of shading in a sense, the translucency, it's like a 50% translucent. So the more concentrated the color, that more like the more data like for that site. And to kind of show you what this looks like in an actual grain, this is an image from the SEM, and you're seeing a giant old grain of naturalinite, and all that gray stuff is just regular old naturalinite, but the kind of white streak through the middle, that's iron-rich alunite. So it's, it's compositionally still naturalinite, but it's got a lot more iron in that rather than aluminum entirely in its B site, and that has an Fe number in the center, kind of the most iron-rich of about 16. So kind of the big takeaway from this is that Fe number varies between and even within grains from the same sample. There's a lot of variability in where that iron is located. But then the question is, how does that affect whether we're going to be able to identify it with instruments that we have on Mars? So now I'm going to briefly talk a little bit more about XRD. Which is just that it uses Bragg's law, essentially. We send in an X-ray with cobalt or copper, so we know the lambda, the wavelength. It comes out a certain angle, and from the angle we can determine the spacing between the mineral layers. So minerals are crystalline solids, so they've got characteristic spacing that we can use to kind of understand the mineral and determine what mineral it is. So I'm still showing you that formula, and essentially what I'm showing you is several naturalinite standards plotted up here based on their Fe number. And although obviously it's very small differences, we're talking angstroms here, there is a significant variation, an increase with Fe number of that spacing between the mineral layers. So this is something that Curiosity could actually do. This is something that Chemin data will give us that we can actually determine if we're looking at a pure jarosite or we're looking at something that's intermediate, something that's between alunite and jarosite. So to talk briefly about the implications, yes, iron-rich naturalinite was found at pretty much all of these different sites. Furthermore, that iron-rich alunite was forming at pHs of up to 5, and jarosite, if you recall, was forming only at pHs of maybe up to 3, maybe 4 if I'm generous. So that means something different about the ancient environmental conditions. And lastly, we can use XRD to distinguish between the alunite and the jarosite species on Mars. So lastly, I'm currently using also some Raman data I've collected to try and see how the peaks are shifting relative to the Fe number. Unfortunately, each peak shifts slightly differently, so it's not quite as straightforward as with XRD, but that's something I'm working on figuring out. And I'd like to thank my advisor and these pair of pants I ruined when I sat a funeral, and it's going on to next slides, but and thank you all for listening.
Any questions for Laura? Got one in the back.
Oh yes. Have you think about the Suchmanite pace? Because 2 years ago, MSL got several XRD data from Mars, but there's no jarosite and alunite. But amorphous space have a lot of iron and surface phase.
What?
Do you know the Suchmanite?
Space? What are you? Sorry?
Do you know Suchmanite mineral pace?
Shortmanite.
Suchmanite.
Yeah, I haven't heard of any shortmanite on Mars. I don't know if anyone has found shortmanite on Mars, but to my knowledge, that hasn't been.
Because 2 years ago, the MSL got XRD data from Mars surface, but there's no jarosite and alunite.
There is, so actually we've had several, there's at least several papers now out on the XRD results. They've done XRD on, I want to say, at least 6 sites on Mars. Some of that data hasn't been published yet. But at LPSC and at AGU, they shared that they found jarosite at Confidence Hills. So that's at the base of Mount Sharp. I'm eagerly waiting for that data to be published so I can kind of investigate a little bit further about whether that's jarosite or alunite or something in between based on their XRD data. I know it's going to go up on whatever that PDS or whatever that website is eventually, so I'm eagerly waiting that.
Oh, I see. I didn't see jarosite in XR data, so
Yeah, that's pretty new. That was presented at AGU, I want to say, this year. Yeah.
Well, thank you.
Hi, great talk. I have a question about the slide where you show different iron concentration in the 3 sites. Yeah,
This?
that one.
Okay.
It looks like iron only substitutes in the high temperature acidic environments a lot. Do you have an explanation?
You know, I actually didn't really think about that. That's a good point. On the other hand, at the dome edge, I don't know if you can tell, but that top point is actually I think 5 or 6 data points are kind of concentrating that top point, which is about Fe number 15. And that's at much lower temperature. We're talking 30 to 45 degrees Celsius. So I don't know if there's any correlation there. It would be interesting to find out why iron substitutes in alunite. And that's definitely something for further research to understand why that happens. And if temperature and pH are involved in that. Even more, yeah.
Get one last question here.
Very good talk. So I just have a quick question. You show that the relationship between D and composition. In XRD pattern, there are many peaks, right? Mm-hmm. What particular peak did you pick it up? That particular D value. Do you know the?
Which particular peak?
Right, yeah.
Yeah, let me try and remember which peak. Oh boy, when I put this together. I think I chose several different peaks and they all pretty much looked the same, no matter which one I chose. The plot looked pretty similar. I'm trying to remember which specific one I chose. I'm guessing I used the one that's it's about at 2 theta of 17 for jarosite. I'm using a copper XRD and about 18 for alunite is I think the one I used because it was easy. But you can also use the one that's around a 2 theta of, oh my gosh, it's just continuing on still. You can also use the one that's a 2 theta of around 30. Yeah, there's several different peaks you can use.
Right, for publication, you need to make it specific, put a middle index over there so people can correlate your data with other people's data.
Yeah.
Right.
Yeah.
All right, let's thank Laura once again.